This course is an introduction to time series forecasting with Python. You'll learn what time series data is and how to break it down into its key components, like trend, seasonality, and residuals. You'll start by building simple baseline models before learning about powerful forecasting techniques such as ARIMA and seasonal ARIMA. You'll discover how to forecast future values, evaluate your models using cross-validation, and incorporate exogenous features to improve predictions. The course also covers how to generate prediction intervals and select the most appropriate evaluation metrics for your projects. You'll gain a clear understanding of the main forecasting techniques and how to apply them in practice. And you're in good hands. Marco teaches this course, and he wrote an entire book on the topic.
Hello and welcome to this video. If you are new here, let me just quickly introduce myself. My name is Marco, and I am passionate about teaching and about time series forecasting. Okay, so I currently work at Nixla, which is, in my opinion, and even before I joined the company, one of the leaders in open source time series forecasting software. And over there, I get to work on Neural Forecast, which is our package for forecasting with deep learning models, and also get to work on TimeGPT. So very cool stuff. I also wrote a book on the subject, as you can see here, time series forecasting in Python. So I wrote this book. I'm very proud. There's actually a second one coming at the end of 2025. And there's also a blog that I have where I share my best tutorials on forecasting with Python. Now, enough about me, okay? If you are here, it means that you are interested in time series forecasting, and this is the best starting point for you, okay? We're going to cover everything that you need to know to get started in the field of time series forecasting. So perfect video if you know how to code in Python, you've done some data science projects here and there, but if you've never really handled time series data before, don't worry, we're gonna cover everything that you need right now. So let's not waste any more time, let's jump right in. So a good starting point when learning forecasting for the first time is by studying the statistical models, okay? First of all, because they're still good models, they're still relevant today, and because it also builds the foundation knowledge that you need to then start using more advanced machine learning and deep learning techniques, all right? And of course, if you are interested in those, more advanced, more recent techniques, let me know in the comments or by liking this video. So on the agenda for this lesson, we will quickly explore the fundamentals of time series data, okay, so defining them, looking at its components, and then we are going to develop baseline models, all right? Those are super simple models, but very important to have. And then we start forecasting with the ARIMA model, all right? After that, we are going to explore some more advanced techniques in forecasting, so things like cross-validation, working with exogenous features, all right, generating prediction intervals. And finally, we are going to see how we can evaluate those forecasting models. And so, as you can see from this video, we're going to get a complete picture of forecasting. Only here we are focusing mostly on using statistical models. And of course, everything will be coded in Python. So let's start by defining time series, all right? And a time series is super simple. It's a set of data points ordered in time. And ideally, the data is equally spaced in time. So you have, data every minute or every hour. And so there are many examples of time series, right, that we see day to day. For example, the closing price of a stock, the electricity consumption of a household, or even the temperature outside. Okay, so as long as your data is indexed in time, it can be viewed as a time series. And here, for example, I show you an example of time series, which in this case tracks the monthly milk production in Australia. So every month, we are going to record how much milk is produced. And now, take some time to analyze this graph, okay? Feel free to pause the video and analyze this graph a little bit. And notice that there are two things, right? We see there's a trend in data, so the milk production is increasing over time. And there's also a repeated pattern, right? So we see it's like peaking and then dropping down, peaking and then dropping down. And this is being repeated every time, right? And so this pattern is what we call the seasonality, okay? It represents a cycle that is repeated at a fixed time intervals. And we can actually decompose most time series into the components I just mentioned, okay? So at the very top here on the graph, you see it is our original data. And then the graph right below it, it is the trend, okay? And the trend, we define this as like the general direction of our series, okay? And so we see that the trend is slowly increasing over time, right? And then the third graph, this is where we have the seasonality, okay? Which is again, the pattern being repeated at fixed time intervals, okay? So we see the same pattern being simply repeated time and time again across our series. And then finally at the bottom, so whatever is not explained by the trend and the seasonality is what we call the residuals, okay? And those represent quick changes in your series, okay? That are not explained by the first two components, right? And ideally, those changes are completely random, all right? So when you are forecasting time series data, you're really trying to model and forecast, the trend and the seasonality, all right? Because those are mathematical components that you can actually model and forecast in the future, okay? Assuming that your residuals are completely random, this is stuff that is not captured by a model, right? It is impossible for us to forecast, like to predict a next random value, right? Because by definition, it is random, okay? And so this is why our forecast will never be perfect, okay? So we can model the trend, we can model the seasonality, but then the residuals, it's always going to be the errors left after our models, all right? So with all of that in mind, let's start forecasting using baseline models. And a baseline model is crucial, okay? It is a very simple model based on some kind of heuristic or statistic, okay? Usually includes, using the mean of your series, using the last known value. This is what we call the naive forecast. Or we can simply repeat the last season of data, which we call the seasonal naive forecast. And so to give you an example, here are some baseline models for our milk production dataset, okay? So here, the first forecast that you see, so what I did is I reserved the last 12 time steps just to say, we're going to forecast the last 12 time steps and we can compare the predictions versus the actual values, right? So the line that you see right here, this is simply the historical mean, okay, for the next 12 months. So what we did is took the entire data set, we calculated the mean, and then we said, well, that value is going to be the same for the next 12 months, all right? Nothing exciting, it's just a flat line, right? That represents the average of the series, but this is one of the baseline models that you can use in forecasting. Now we can be slightly smarter about it, right? We can realize, well, data that is very old, very away in history might not be as interesting as the most recent period, right? Because, I know I have a trend, my milk production is increasing. Why would I care about what happened in 1960s when I'm trying to forecast 1976, okay? And so you can also take the mean over a more recent period. And this is what I did here. So here I'm using the mean of the last year only. And already we can see it's a better forecast, right? Because now we have some overlap with the actual values. And like I said, it makes sense, okay? What happened a long time ago might not be as useful to forecast the future, okay? And then we add the naive forecast, which here is simply repeating the last known value into the future, okay? Super simple, baseline, very useful, often used as well. And finally, we can simply repeat the last season of the data. And so in this case, a season, it lasts 12 months, all right? So because we have monthly data, the season is being repeated every year. So what I did is I simply took the last 12 months of data and I repeated it into the future. And as you can see, we can barely see the line on the graph, right? Because it overlaps almost perfectly with the actual data. So the lesson here is make sure to have a baseline model and also be smart about the baseline model that you are using because it can be a really good model, okay? And your baseline must be really good so that you're really challenging your more advanced models that you're going to spend time tweaking and tuning and selecting, okay? So it's really important to have a good baseline so that then you can make a very good comparison with your more advanced models and then justify, like, yes, this model that I designed is much better than something really simple and naive, okay? So, at this point, it's time to jump into some code, okay? So write some Python code to make those baseline models come to life, and then we are going to come back to the slides to learn a little bit more theory. Alright, so let's get started with some code. I am right now working in a notebook, so if you want some instructions on how to set up the environment to reproduce the results I am going to show you, I have the little instructions right here. So either for local development, so you can create your own environment and install the required dependencies, or the easiest way would be to start a Google Colab notebook and then just install the following dependencies. Don't forget that on Google Colab, you already have the basic stuff like pandas, numpy, matplotlib, etc. So really you only need to install stats forecast and utils forecast. And of course, at any point, if you want to see the full solutions, you can head to the GitHub repository. Of course, all the links are going to be available below the video. So we are doing this one right here, YT03 forecasting stats. So this is the entire solution. And the data set is in the data folder. So the daily sales French bakery.csv file. This is the data that we're going to be using for this tutorial on forecasting. So let's not waste any more time and import our dependencies. So of course I'm importing the usual NumPy, pandas, and matplotlib. I am also using utils forecast. So utils forecast, this is going to be very useful for us to plot our series, also to evaluate them using different metrics. And the metrics are coming from utils forecast.losses. So of course, more information on that as we go through the tutorial. Then I am going to read my data, and in this case, I am reading the data locally, okay, but of course you can put the URL of the GitHub repository for the CSV file, right? So you can always replace this data / daily sales, you know, so if you just go here in data and then you click on the CSV file, and then once that loads, you can click on raw, and then you can just copy paste the URL that you see and paste it here, right? And it's going to do exactly the same. So here we're just doing a little filtering. So I am just taking the series that have more than 28 time steps. This is going to be useful for us because we're going to be doing some testing and cross-validation as we go through this video. So this is why I am filtering right now. And then I am also dropping a column called unit price. We'll go back to it in a moment when we are ready in the tutorial. And you should get the following. So we have 3 columns, unique ID. So this simply identifies what series we are looking at. And of course, keep in mind, we are looking at the sales of a French bakery. Then we have the DS, which is the date stamp, so simply the date, and Y, which is the value, so the volume of the sales for a particular product, okay? Now, in this case, there are many products in this data set, okay? And here I am just plotting 2 of them. So we have the sales of baguette and croissant. So as you can see, we have the sales throughout many months. This is a daily data set, right? So every day we have a new data point. And as you can see, sometimes it falls to 0, sometimes it's not really equal to 0. And then also here for baguettes, the scale is different, right? So we oscillate between 0 and 100. Whereas for croissants, we are oscillating between 0 and 300. So something to keep in mind as well. And then the nice thing about this plot series function that comes from utils forecast is that you can zoom in using this max in sample length equal to 56. So now as you can see, now we are only plotting the last 56 time steps for both baguettes and croissant, all right? So I am not spending too much time explaining the plotting functions. Okay, we are going to be doing plots, of course, but I don't want to spend too much time on them simply because I want to focus this tutorial on forecasting time series, right? And using stats forecast to make good forecasting models. So feel free to, to pause the video and study the plotting code a little bit more. But again, this won't be the focus of this tutorial. So with all of that being said, let's get started with some baseline models. And so in this case, we are going to be using stats forecast, of course. So this is, in my opinion, one of the best and of course, and also the fastest implementations of statistical forecasting models. So definitely something you should be using. And luckily for us, they have all of the baseline models already implemented. So the naive, historic average, window average, and seasonal naive. All right. So let's take a look at how we can define them. For this situation, I will set the horizon equal to 7 because we have daily data. I think it is reasonable to expect to forecast the sales for next week, so for the next 7 days. But of course, this is entirely subjective. Okay, I decided that. I don't know if this data set was necessarily built for a forecast horizon of 7 days, but we'll just go with this. And then the way this works is we are going to define a list of models. So with stats forecast, we can fit many models at the same time, and we can just pass a list of the models that we want to fit right away. So we will use a naive model. So remember that the naive will simply forecast the last known time step. Okay. Then we can have the historic average. So this is going to take the average of the entire history of our series and then use that value as a forecast. We can also have the window average. So window average, and then you can specify the window size. So how many time steps do you want to take into account to calculate that average and then forecast that value? So here in this case, I will set a window size of 7. This means that I will look at my data set and then I'll take the average of the last 7 days and then forecast that into the future. All right. And then finally, we have the seasonal naive model, and now we need to specify the seasonal length. So here in this case, what is the length of my season? So if I go back up here, clearly we see some kind of seasonality every 7 days. This is pretty usual for daily data, right? So in this case, we have a seasonality of 1 week. 1 week is 7 days. So the season length is also going to be equal to 7. Great. Now that this is done, we are going to initialize our stats forecast object. So this is going to be the object responsible for training, fitting, predicting, cross-validation when we get there, etc. So we always start with that. And then we pass in the list of models that we want to fit. So here in this case, models is going to be equal to models. And then you specify the frequency of your data. So here in this case, the frequency is daily. So we pass in capital D. All right. So this basically takes the frequency strings similar to pandas. All right. Once that this is done, we're going to call the fit function. So you're going to fit, and we're going to fit on the entire data frame like so. And then you can make some predictions. So I'm going to say the print is going to equal to sf.predict. And then you need to specify the horizon. And so here in this case, the horizon is equal to 7. And we can run this. As you can see, this is almost instantaneous, right? This makes sense. There's no real fitting for these models, right? We're using very simple statistics and logic to make very naive predictions. But you can see what the predictions look like, right? So as you can see, for each time series in our data, right, we have made predictions using the naive method, historic average, window average, seasonal naive, and so on and so forth, okay? And of course, we can now plot those predictions. In this case, again, I am plotting the predictions only for baguette and croissant, and you get the following. Now, of course, this is nothing amazing, nothing exciting, right? 3 of our forecasts are simply horizontal lines. This makes sense, right? This is the naive, historic average, and window average. And then we have the seasonal naive, which simply repeats the last 7 days of our data, all right? So again, nothing crazy, but this is potentially your first forecast, right? If you are getting started in forecasting time series. So you have made your very first forecasts. Now, we have predicted the future, right? However, we do not know how those models are performing, right? Because we made predictions for time steps for which we don't know the actual value. So we cannot compare the predictions against actual values. So let's redo this exercise, but now we're going to do a test train split, okay? So I'm going to say that test is going to be equal to df.group by, we're going to group by unique ID. And then I'm going to take the last 7 time steps as a test set, okay? So for each unique ID in my data set, I'm going to reserve the last 7 time steps for the test set. And then of course, train is going to be the rest of that. So it's going to be df.drop. We're going to drop test.index, and then we are going to reset the index like so. Great. And then once this is done, we can redo our fit and predict. So I'm going to do sf.fit. This time I'm passing the train as the data frame. And then my predictions are going to be equal to sf.predict, where h is going to be equal to horizon. And then we're going to create our evaluation data frame, where I have both the actual values and the predictions. So I'm going to say that evaluation df is going to be equal to, so we're going to merge the two data frames. So pd.merge, we're going to merge the test data frame as well as the predictions data frame. We're going to do a left merge, and we're merging it on the date stamp and the unique ID, like so. So let's run this again, super fast. This is done. And now we have our evaluation data frame. So now how are we going to evaluate? We're going to use utils forecast. So we're going to say that evaluation is going to be equal to the evaluate method. So this method comes from utils forecast. We need to pass the data frame. So the data frame that contains both the predictions and the actual values. And then we can specify what metrics do we want. In this case, we're going to use the MAE. All right. The MAE is something, let me scroll back up quickly. This is what we imported here. So I imported star. So I am importing all of the available losses from utils forecast. MAE is part of it, which is why I have access to it right here. All right. And the MAE is super simple. It's the mean absolute error. Okay, so we just take the average of the absolute distance between the predictions and the actual values, and then we take an average of all of that. So this is what we are going to use right here. And then you can inspect the evaluation data frame, and you should get the following. All right. So as you can see, for each series, we now have the MAE for each of our methods. So for the baguette, naive got an MAE of 17, historic average an MAE of 5, window of 7, and then seasonal naive 12. And you see we get that for every unique ID of our data set for each model. Now, we have a lot of time series. Like I said, we have a lot of unique IDs. So something that would be interesting would be to average across all of the series, right? To get like an overall idea of the performance of each model. So I'm going to say that evaluation is going to be equal to evaluation. And then we are going to drop the unique ID. Axis is going to be equal to 1. And then we are going to group by the metric. And then we're going to take an average of that. And then we'll reset the index. And now we can display evaluation. So this will give us the average of the MAE for each unique ID and for each model. So once you do this, we get the following. So now we can see that naive on average across all of the series gets an MAE of 6. Historic average 5, window average 5, and so on, okay? And then right here, like I said, this is some plotting code that I already have written out, just so that we save some time here, and you get the following. So it's just the same metrics that I showed above, but shown as a bar plot. So clearly, as you can see, seasonal naive achieves the lowest MAE across all series. This makes sense, right? Our series, from what we have inspected, they do have some seasonality to it. So again, you can see that with seasonal data, using the seasonal naive baseline is usually the best baseline. And so this will serve as a benchmark for our future experiments throughout this tutorial. All right. So that's it. That's it for this portion of the code. Let's go back to the slides and now learn about the ARIMA model. All right, so at this point, we have used Python to forecast using baseline models. Okay, I know nothing super exciting just yet, but now let's introduce a more advanced model. And so here, there are, of course, many statistical models that we can use, all right, and each of them has its own strengths and limitations, right? So the ARIMA model, the one that we are going to look at in this video, is one of the most fundamental models, okay, and it can handle seasonal data and exogenous features, which is why I decided to use it for this tutorial. We also have exponential smoothing, works well on seasonal data. We have the theta model, which uses decomposition to make predictions. This is actually a very good model, and recently has won, not that it has won, but it has come very close to winning in a forecasting competition. Then we have some more advanced models like MSTL and TBATS. Those models, they can take into account multiple seasonal periods. And then we have models like Croston, IMAPA, and TSB, which are specifically built for intermittent time series. So that means when you have data with 0 values and then not 0 values, super important there. Now for this video, we're going to focus only on ARIMA, like I said. So if you want to learn about the other models and more advanced techniques, then I suggest that you check out my course, Applied Time Series Forecasting in Python. There is a link with a discount code in the description, and in that course we're going to cover all of the models and of course much more advanced techniques. So it's there if you are interested and you are willing to really master time series forecasting. I suggest that you take a look at this course. But for now, like I said, we're going to explore ARIMA. So ARIMA stands for Autoregressive Integrated Moving Average Model. So AR is the autoregressive portion, I is what we call the order of integration, and MA is the moving average portion. And so with ARIMA, you can really forecast any series that has a trend and a single seasonal period. Okay, so if your series has more than one seasonality, you have to use models like MSTL or TBATS, but if it only has a single seasonality, ARIMA can handle that. So let's break it down a little bit more, okay? AR, the autoregressive model, it is basically a regression against itself. So it is really saying that future values depend on past values. It's pretty logical, right? And the mathematical notation is ARP, where P is what we call the autoregression order. Now, autoregression order simply controls how many past values do we consider. Okay, so if P is equal to 1, then as you can see, we only do a regression against YT minus 1. So current time step is YT minus 1, the time step before. If we set P equals 2, then we look at the past 2 time steps. So YT minus 1 and YT minus 2. Simple as that. Next, we have the moving average model, the MA portion, okay? So MA says that future values depend on the present and past error terms. So basically, this model is saying that the series has some kind of an average value, and then it is bouncing up and down from that average due to some random error terms, okay? And those error terms are what we're going to use to forecast the series. And again, mathematically, we denote it as MAQ, where Q is the order of the moving average process. So here, if Q is equal to 1, that means that you are looking, at the past error term, so at T minus 1. And if Q is equal to 2, you're looking at the 2 past error terms, T minus 1, T minus 2, fairly simple. Now, when we combined the autoregressive and the moving average models, we get an ARMA model. Okay. Problem is, this model only works with stationary series. Okay, meaning that the series has no trend and no seasonality, mostly. Okay, not very useful. All right, we are mostly interested in series with some kind of seasonal pattern and some kind of trend, right? And so, if you want to use the ARMA model, you have to make transformations to your series. So we don't really use that anymore. So we use the integration order I, okay, which will internally transform the series to make it stationary. So that way, you don't have to make the transformations. You can simply model non-stationary series directly with the ARIMA model, all right? And usually D is set to a value of either 0, 1, or 2. But anyway, we don't spend too much time on those parameters because as you will see now, we have methods that automatically optimize those parameters for ourselves, okay? So let's not spend too much time here trying to know what the best value of each parameter is. Now, ARIMA is great, but if you want to model seasonal series, we adapt the ARIMA model and call it the SARIMA, okay? So the seasonal ARIMA. And this is going to include new seasonal patterns, okay? Seasonal parameters, right? So now you have capital P, which is the seasonal autoregressive order, okay? And it's going to look at multiples of the seasonal period, all right? So we're going to see in a minute what that means. And then same thing for capital D, so the seasonal order of integration, and capital Q, the seasonal order of the moving average portion, all right? And then you have the frequency, super important, okay? The frequency is the number of observations per cycle, all right? So that was a lot of information. Let's take a look at an example to understand all of that. So we go back to our example of milk production, okay? So here our period, or the length of a season, right, is really 12 months, okay? Because as you can see, we have monthly data, right, on the graph, and that pattern is being repeated every 12 months, okay? So our season length, our frequency, is equal to 12 data points, all right? So if we have now a capital P, okay, of value 1, it means I'm going to take a look at the value at t minus 12, okay? So what was my value 1 year before, or 12 months before, okay? Same thing for capital Q. So what was the error term 12 months before the present time step, okay? So this is how those seasonal orders and parameters work. So, with all of that in mind, let's take a break from theory, go back into the code, and start modeling with the ARIMA model, okay? Because in practice, all you really have to do is set the frequency of the data, okay, or the season length, all right? The rest, we're going to use what we call the auto-ARIMA function. That is going to find all of the optimal parameter combinations of, you know, small p, small q, capital Q, and even lowercase d, capital D, right? So it's going to automate that for us and select the best combinations automatically for us. So really all we have to do is provide the seasonal length, and that's it. All right. So let's jump back into the code. All right, and we are back into the code, and now we are going to forecast using the ARIMA model. And specifically, we are going to use the auto-ARIMA function because, like I said, we are not going to optimize the parameters ourselves by hand. Now we have auto-ARIMA functions that can do all of this optimization for us, and so really we should use it. So first of all, I am going to define a subset of my dataset. Why am I doing that? This is because with statistical models, when you have multiple series, you are fitting one model per series, okay? And in this case, we have quite a few of unique IDs. I don't remember the exact number, but we have quite a few hundreds of unique series, okay? And so while StatsForecast is very fast, okay, ARIMA itself is not that fast. There are other models that are much faster than ARIMA, so exponential smoothing, MSTL, and stuff like that. They will be much faster to optimize than ARIMA. So in this case, we are going to be working with only Baguette and Croissant, just so that you don't have to stare at your computers for, you know, many minutes waiting for a model to train, okay? So this is the only reason I am doing this, but of course, feel free to train on everything or select other unique IDs. Really, the goal here is to make this project your own, all right? So now I'm going to define a subset of the train set. So I'm going to call it small train. So small train is going to be the training set that we had earlier, where the unique ID is going to be in unique IDs. And then we'll do the same thing for test. So small test is going to be equal to test, where test dot unique ID is in unique IDs. Great. Once that this is done, we are going to define our list of models, okay? And here I am going to try out two different models, okay? So I'm going to try out the auto-ARIMA, but I'm going to set seasonal equal to false, okay? And the alias, so the name of this model, I'm going to call it ARIMA, all right? So I just want to make this little experiment with you where we're going to fit either an ARIMA model, so without the seasonal component, and we're also going to fit an auto-ARIMA model where now we allow the seasonal component, so we specified the seasonal length in this case, right? And so we are going to see which model version performs best in our scenario. Now you should have some kind of a intuition that because of seasonal naive, it already performed better than the other models. Likely using a seasonal ARIMA model is going to work better as well, but still, let's just do this experiment right now so you can also see how you can do that yourselves later on. So after that, of course, initialize your stats forecast object, pass in your list of models, and then the frequency is still daily. After that, you are going to fit on the small training set, right? Otherwise, like I said, it's going to take quite a bit of time. And then we're going to make some predictions. So I'm going to say that ARIMA preds is going to be equal to sf.predict, and h, of course, we keep our horizon of 7 days. Once we have our predictions, we can make our evaluation data frame, right? So ARIMA eval df is going to be equal to pd.merge the ARIMA preds with the eval df. And then we're going to do an inner join, and we also join on ds and of course unique ID. So that way we are going to be able to compare the predictions of all of our baseline models plus now the ARIMA and SARIMA model. So after that we can evaluate. So ARIMA eval is going to be equal to evaluate, and then we pass the ARIMA eval df, and the metrics will stick with MAE. All right, simple as that. So after that we can display the evaluation data frame. So let's run this. Like I said, this is going to take a bit of time because it's going to run the optimization of ARIMA and SARIMA for both series. So like I said, it's going to take a few minutes. So I will be back once it is done. And I made a small typo here. Metrics should be, I forgot the equal sign for MAE. So sorry about that. It didn't take that long actually to fit everything, but I made this little typo. So now I will be back once this is done. All right, and you get the following. So as you can see, now we have our evaluation data frame for our both series, baguette and croissant. And we have now the metrics for ARIMA, SARIMA, and all of our baseline models. So again, this is per series. So if you want to have the average for everything, we can run the same logic as we did earlier. And now you get the metrics for the models overall, right, for all of the series. And you can see basically that SARIMA is the best model, achieves an MAE of 8.9, ARIMA 11.9, but still both models are now better than any of the baseline models that we used earlier. All right. You can also plot the series if you want. So now we can visualize the kind of forecast that we got using SARIMA and ARIMA. And as you can see with SARIMA, which is the yellow line, we get a much better sense of the peaks, right? We were able to forecast that better versus ARIMA, where we force the model not to use any seasonal components. And as you can see now, it is struggling much more to make accurate forecasts. But again, it makes sense, right? We have a seasonal series, so it makes sense to use the SARIMA model. I just wanted to make this experiment with you so that you can see those types of results and how it looks like and how you can do it as well. So then comparing the metrics for all of our methods that we've used right now. Again, keep in mind, we are only evaluating on the last 7 time steps of our data. So here, of course, the worst model is the naive model, achieves the highest MAE. And now our best model right now is SARIMA model. But like I said, we are only evaluating on the last 7 time steps. This is not a great test set, right? So a much better way to evaluate our forecasting models is to run cross-validation. So let's go back to the slides, learn about cross-validation, and then we'll come back to the code to implement it. All right, so we have done some forecasting with ARIMA. We even compared ARIMA versus SARIMA. But now let's explore one of the most important concepts in time series forecasting and data science in general, really, which is cross-validation. So by now, you might have noticed, right, evaluating on a single forecast period, right? So on, just a few days, for example, is definitely not enough, right? There are too few data points, so it's not really representative of the model's performance. And so this is why we need a more reliable and robust evaluation, and this is done through cross-validation. Now, if you have some background in data science or machine learning, right, cross-validation with time series data is a little bit different because now our data is ordered in time. And so we need to keep that order fixed in time, okay? You cannot start shuffling your data around, okay? It has to stay in that order. And so with cross-validation in time series, okay, we start with an input window. This is what you see, the darker window here on the left. And then you are going to make prediction over a certain horizon, so the light blue window that you see. And then once this is done, you're going to update your input sequence, and then you are going to forecast the next window, all right? And that process is repeated until you either run out of data or you reach the maximum number of windows that you desire, all right? And so as you can see, this really mimics the situation where I'm going to forecast a certain horizon, I'm going to wait for new data to come in, and now I'm going to use this new data as an input to my model to make the next set of forecasts, all right? And this is how you should really evaluate your forecasting models, okay? So you need to use cross-validation to forecast multiple windows, and now you get, many windows of predictions versus actual values, and then you can evaluate your forecasting model, and you get a much better picture of its performance and how it would perform in real life, all right? So fairly short, okay, but that is it. This is cross-validation. So let's go back into the code and see how we can apply this method. All right, so let's run cross-validation such that we have a much more robust and representative evaluation of our models, okay? So here in this case for cross-validation, we don't need a train test split anymore because we're going to be using different windows of forecasts to make the evaluation of our models. So I actually want to pass the entire data set to cross-validation because that function internally will take care of creating the windows, making forecasts, updating the input, making the next forecast, and so on and so forth. So I will say that small df is going to be equal to df where the unique ID is in the small list of unique IDs that we defined earlier, right? So baguette and croissant. And then we're going to specify the models again. So I'm going to say that models is going to be equal to, in this case, we'll use the seasonal naive because this was the best benchmark as we saw. So I'm going to say that season length is going to be equal to 7. Then we're also going to try the auto ARIMA model. I'm going to say that seasonal, let's set it to false, this one. So again, we're going to use an ARIMA model, even though I think this one will not perform very well. And then we'll also use the auto ARIMA, but this time we'll allow this to be a seasonal model. So seasonal length is going to be equal to 7. And the alias, let's set it to Sarima. Of course, this must be a string. All right. Then once this is done, you initialize the stats forecast object. By now, you should be comfortable with it. So you pass in your list of models, and then your frequency is still daily. And now we are ready to run cross-validation. So I'm going to say that my CVDF, so my cross-validation data frame, is going to be equal to sf.cross-validation. So now let's take a look at the cross-validation method. First, we need to define the horizon. Okay, so how many time steps are you forecasting? So in this case, it's still 7 days. You pass in your data frame, and this time I am passing the entire data frame because like I said, internally, it will make those windows for us, okay? So speaking of windows, how many windows do we want? In this case, I'm gonna set it to 8. Why am I doing 8? Because with an horizon of 7, we have 8 windows of 7 forecast. 8 times 7 is 56. And so with that, you get at least more than 50 points, right? So 56 points per series to evaluate. So this starts to be a reasonable sample size to get an evaluation of your series. Of course, the more windows, the better, right? But here in this case, I am sticking to 8. And then we're going to set the step size. So the step size, this basically determines the distance between the starting date of each window, all right? So here I like to set the step size equal to the horizon. That way we do not get overlapping windows, okay? So the windows are going to be one after the other. If your step size is less than your horizon, you will have overlapping windows, all right? It's not necessarily a problem. Just know that you will have more points, more time steps being forecasted more times, okay? And so you might give more weight to those time steps when making an evaluation, okay? So just something to keep in mind. Usually, I believe that for most situations, using the step size equals to the horizon, so you have non-overlapping windows, is the best way to go. It's also going to be the fastest way of running cross-validation. So I think you should stick with this. And then you have the refit parameter. So this is something entirely up to you. The refit parameter determines if you want to re-optimize your model, like refit your model, every time the input size changes, okay? And that really depends on your use case. If you think that your model is going to be updated every time you're going to make forecasts and every time you get new actual data, then you should set refit equals to true. However, if you think that you're going to train your model once and then you're going to run forecasts, for a while, and then just after, 3 or 4 months of the model being in production, then you are going to refit, then you should set this parameter to false, okay? Of course, setting it to false makes the entire process much faster. Setting it to true makes it slower because, of course, you're going to be re-optimizing, refitting your model for every window, but then it might give some better performances, right? And here clearly I have made a typo, so it was stats forecast. Sorry about that. Great, so now this is gonna take a bit of time to run because again, we are gonna be fitting 2 ARIMA models per series, but we're also doing that multiple times because we said refit is equal to true. So we're doing that for every new window of data. So we will be back once this is done running. All right, and now our cross-validation is over. It is done running. We can of course make some visualization of the predictions that were made, and we should get the following. It's a little bit hard to see on the screen what is happening, right? But basically the yellow line is still the ARIMA model. We have the naive as a slightly lighter blue, and then we have the ARIMA model as some kind of this blue-green, okay? But anyway, all that to show that we have now made predictions over a longer period, right? Over multiple windows, I should say. So it's still 7 days forecast, but we've done that multiple times, 8 times to be precise. So now we get more points to compare, right, against the actual values so that we have a better evaluation. So let's run that evaluation right away. So I'm going to say that CV eval is going to be equal to evaluate, and then you're going to pass the cross-validation data frame. But in this case, I'm going to drop 2 columns. We'll drop the cutoff column. Access is equal to 1. So sorry, I said we're dropping 2 columns. In this case, we're only dropping 1. So we're dropping the cutoff, okay? The cutoff simply says this is where the model stopped training. So you should see basically this is the forecast for the 6th of August. So it stopped at the 5th of August, and same thing for the 7th of August. It stopped training at the 5th of August, okay? So this is what the cutoff date says. It just says where the model stopped training, so stopped seeing actual data. So we're going to drop that column because we don't need it. And then I will say that metrics is going to be equal to MAE as usual. And then I will say that my CV eval is going to be equal to CV eval.drop. By now, you know what we're going to do. We're going to drop the unique ID. And then we're going to group by the metric. We're going to take the average, and we're going to reset the index. And then we can display the evaluation, and we get the following, okay? Now, of course, we can visualize that in this bar plot, and you should get the following result. Now, interestingly, the ARIMA model, so the non-seasonal ARIMA model, is worse than seasonal naive, okay? So here, that's super interesting, right? So this is why we need to have good baseline models, okay? The seasonal naive is actually better than our trained and optimized non-seasonal ARIMA model, all right? And also now, I hope that you see the importance of doing cross-validation, because before, we thought ARIMA was better than seasonal naive. But now, when comparing multiple forecast windows, so on more data points, we are seeing that on average, seasonal naive is actually better than ARIMA. However, SARIMA, okay, so our seasonal ARIMA model is better than seasonal naive, and of course better than ARIMA. This makes sense. We have seasonal data. It was expected that this model worked best. And now we have this confirmation as well, right? That even on multiple forecast windows, SARIMA still performs better than our baseline, all right? So that's it for cross-validation. Again, cross-validation is a critical point and critical, method to know when doing time series forecasting for more robust and representative evaluations. So that's it for cross-validation. Next step is working with exogenous features. Okay, so up until now, we have only used past values of the series to make forecasts. That's great. It works really well, right? But it is possible that we may benefit from using information of external variables or exogenous features. So let's see how we can do that right here. So like I said, exogenous features are external variables, okay? They are not part of your time series itself. So it could be an entire series, okay, completely. It could be the dates of upcoming holidays, or it could be any external factor to your series, all right? So for example, let's take the example of forecasting the electricity consumption, right? Now, it might make sense to include information about the temperature outside, okay, or the wind speed, or even the hour of the day. Because, for example, colder days means that people are going to turn on the heating, and so consumption goes up. Or even the hour of the day, right? If you know that people, they come back to work at around 5 or 6 p.m., then they are likely to start doing chores, so starting the oven, cooking, starting the washing machine. And so again, your consumption is going up, okay? So as you can see, exogenous features can be very important and can be good features to your model and can improve your forecasts. And there are really three types of exogenous features in time series forecasting. We have what we call the static feature. So that one stays constant in time, so something like a product category. Then we have the historical feature. So this is when we know the value in the past, but not into the future, okay? So something like the price of gas, for example, okay? You know what was the historical price of gas, but you don't know what it's going to be in the future unless you forecast it, but we'll see in a minute why that might be a little bit dangerous, okay? And then you have the future exogenous features, okay? So those are features for which you know the values in the past, and also we know them for certain in the future. So an example of that is the dates of national holidays, okay? We know when were the holidays in the past, and we know for certain when will be the next upcoming holidays, all right? And so with statistical models, they only support actually future features, okay? So to use features with statistical models, you need to know their values in the past and also provide the future values over your forecast horizon. Now, like I said, you could technically forecast a feature to use it, okay? However, you might amplify the error, okay? Because we know our forecasts are not perfect, right? So whatever error you have in that forecast, you are using it again to make another set of forecasts. And this is where the error can really be amplified. And so sometimes it's better to remove that feature completely, okay? But of course, it depends on the situation you have to test. Now, if you don't have features in your data, it is still possible to create some by encoding time series information as features, okay? So for example, we can use Fourier terms to describe the seasonality, okay? So Fourier terms, basically a sum of sines and cosines, and those can really encode seasonal information of your series as a feature, and you can then use those features to make predictions. Something else that you can encode is encode the timestamp itself, okay? So you can say the day of the week, the hour of the day, etc., right? So you can just say this is hour 1, 2, 3, 4, 5, blah, 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 all the way to 24, or, you know, the day of the week, you can say this is day 1, 2, 3, 4, 5, 6, 7, all right, and so on. And so with those features, it is possible that your model benefits a little bit from using those features. And the best part is you know them into the future as well, right? So you know, for example, Monday today, right, is day number 1. You know that next Monday in a week and next Monday in 2 weeks is still going to be day number 1. So you can use those features, predict them over the future, right, with absolute certainty. So it is relevant for statistical models, all right? So that's it. Let's jump back into the code and see how we can create exogenous features and use them with our models. All right, so now let's start forecasting with exogenous features, external variables. How can we include them in our models? And luckily for us, no, it's not every model that can support exogenous features, but I specifically chose the ARIMA model or SARIMA model, right? Because I know it can handle exogenous features, so it makes, you know, for an interesting use case for this tutorial. So now I'm just rereading the dataset because if you remember earlier, I dropped the unit price, but now in this case, we are going to consider this as an exogenous variable. So is the price of the product being sold an important feature when forecasting the volume of sales, okay? And if we take a look at the two graphs side by side, okay, so here at the top left, we have the sales volumes of baguettes, and then we also have the price of the baguette as the time goes on, same thing for croissant at the bottom. Now, something that we notice, right, the price increases, you know, for like steadily. It's not a varying time series, so it's not like the bakery is doing any types of discounts or anything. It just seems to be like the price is naturally increasing due to inflation or rising costs, okay? So we will see if that has an impact on the forecasts when we do them later on. So here I'm just gonna be, you know, using the same ID, so baguette and croissant, and I'm also going to, you know, get the subset of my data frame, and we also doing a small test and train split. So, you know, just code that we have already seen, and I didn't want to repeat it necessarily. Now, as I mentioned in the slides, okay, with statistical models, you need to know the future values of your exogenous features, okay? And in this case, the price, it makes sense, right? The bakery can decide to raise or lower the price, so it makes sense to know this price for certain, all right? And so when you are working with these models, right, and these types of features with stats forecast, you need to specify the future values of your exogenous features in a data frame. So I will say that future exog df is going to be equal to, basically the future values are going to be the unit price stored in the test data frame, right? So it's going to be equal to test.drop. So I'm going to drop my y column, like so. And now you can take a look at it, okay? So you should see the following. So now you see for every unique ID and timestamp, I know the price of the product being sold, okay? That's it. This is how your future exogenous data frame should look like for stats forecast. So now let's go ahead and define the models. So here, of course, you're seeing some boilerplate code, right? Some template code that we've done many times now. So I'm not going to write everything yet. This is also a great time for you to maybe pause the video and maybe try to define the model yourself and then run the predictions with exogenous features, or, you know, just follow along with me right now. So I'm going to say that models is going to be equal to, in this case, we're just going to use one model. So I'm going to say season length is going to be equal to 7. By now we know SARIMA is the best, right? So let's just stick with this one right away. And here I'm going to call it SARIMA exog, because now we're going to be using exogenous features and we can compare how those exogenous features impact the performance of the model. And then, of course, the standard initialized stats forecast, fit the model, and then we can make predictions. So ARIMA exog preds is going to be equal to sf.predict. H is again the horizon, so we stick to 7 days. And now you need to pass the XDF parameter. So Stats Forecast wants to know the future values of your exogenous features. And so that goes to the XDF parameter, which is future exog df. Perfect. And here again, I am also fitting the normal AutoArima model, the normal Sarima model, just to compare the predictions. Okay, so let's run this, and I will be back once it is done. Great, and now that this is done running, we can then create our test df. So we're just going to merge all of the predictions together, and you should get the following. So now test df, we have our predictions for each unique ID. So Sarima with exogenous features and Sarima without exogenous features. If you want, we can plot them in a graph. Here, very, very hard to distinguish between them. So basically the lines almost overlap perfectly, right, between using and not using exogenous features. So it doesn't seem to be making such a big difference, right? But of course here we're only forecasting on the last 7 days. So we did this exercise just to show you how you can make forecasts using the XDF parameter, so by providing the future values of the exogenous features. Now, when we run cross-validation, this will actually detect automatically that it has exogenous features, and it will use their future values automatically as well, okay? So this is why I made this little exercise before. So now let's actually run cross-validation so that we get a nice and robust evaluation of both methods. So sf.cross-validation, I will set h equal to horizon, df is small df as usual, but this time it has the unit price inside, and Windows will stick to 8. The step size is also going to be equal to the horizon, or 7 days, and we are also going to refit the model at every window. So let's run this, and I will be back once it is done. All right, and now that our cross-validation is done, and keep in mind we did cross-validation using exogenous features, we can then run the evaluation. So again, same evaluation code that we have seen many, many times, and we get that Sarima with the exogenous feature of the unit price is equal to, we get an IMI of 19.2. Don't worry, in a minute we will compare that with all of the other methods as well, but before that I want to show how you can create features from your timestamps. Because here in this case, we were lucky, right? We had features directly from our data set, but sometimes that is not necessarily the case. So how can you create those features? And here in this case, I'm going to be using utils forecast again to make those features. So I'm going to use Fourier. So we'll use some Fourier terms to encode the seasonality information from the series. And we'll also use the time features function. So this will get, information from the timestamp to say, stuff like day of week, week of year, etc., etc. And we also use the pipeline so that we can create many features in one go. And super important, from functools, we'll use partial. This allows us basically to reuse some functions, definitions in utils forecast. Just makes everything, cleaner and more efficient. So I'm going to say that the features that I want to define, I'm going to have, so as you can see, we'll use the partial function right away. So I'm going to have a Fourier series here for the seasonality component. The seasonal length is going to be equal to 7. And then you can define the number of terms that you want with the parameter k. Now, with Fourier series, right, the number of terms basically determines how many sines and cosines you want to use to encode your seasonal information, okay? Usually setting k to 1, 2, or 3 at most is more than enough, okay? But basically the more you increase k, the more terms you're gonna use, and technically the more precise your encoding will be. But here in this case, the data set is not very complicated. We don't have super complex seasonalities. So really using a k equals to 2 should be more than enough. And then after that, we're going to specify the time features that we want. And so for the time features, I'm going to say that I want the day. I also want the week, and I also want the month. All right. So now we're going to get features that says, this is day number, whatever, 20 of week, maybe 15 of month 2. Okay. I don't know if what I said really makes sense. Okay. So don't quote everything that I said. I don't know if week 15 corresponds to month 2, probably not, whatever, but you get what I mean, right? So those are going to be features that we are extracting from the date stamp directly. So then we can say that small exage df, and you can also specify the future exage df when you are running the pipeline. Okay, so if you are making predictions for time steps that you don't necessarily have, you can also generate the future values, because like I said, those are features that you can know for certain into the future because they're all related to the cyclical pattern and also the date stamp. Okay. So this is going to be equal to a pipeline, and then in the pipeline we're going to pass the data frame, so small df, that way it knows how to compute the features. Features are going to be equal to the features list that we specified above. Frequency is going to be equal to daily, and h is going to be equal to horizon, so that basically we get 7 future values, right, in our future exage df. So let's go ahead and run this, and where did I make a mistake? Right here, this should not have an underscore, sorry about that. And that's it. So as you can see, super instantaneous, super easy. And again, this should be exage, not exaf, sorry about that. And as you can see, now we get the following data frame. So now on top of the unit price, we also have as you can see, we have 2 sine terms and 2 cosine terms. This comes from k equals 2. So this has the seasonality information encoded in those features. And then you have day, the week, and month, right? So for the date 2021-01-02, so the month is January, the week is 53, and then we have day equals to 2. All right? Perfect. And of course, you can also have the future exage df. So as you can see now, those are your future values for each exogenous variable. Great. So now that this is done, let's actually train this model and see how it performs. So here I'm actually not going to rewrite all of the code, okay, because this is stuff that we have already seen. All right. So this is the ARIMA model. But now we are using the time exogenous features, so exogenous features from time features, okay? And then we're gonna run the cross-validation, so same horizon, the data frame that we have on top right here, so this one, unit price with all of the other features that we built. We're gonna run cross-validation, and then we're gonna run the evaluation, all right? So again, this is all code that you have seen. Nothing is new here except the part of creating those features, which we just covered. All right. So I'm just gonna let this run, and I will be back once it is done. All right, and now that this is done running, you can see that we get an MAE of 19.5. So now we can compare all of the methods that we have done so far. So we have the ARIMA model, seasonal naive, SARIMA with time features, SARIMA without features, and SARIMA with only the price as an exogenous feature, and we get the following graph. So as you can see, using the price as a feature actually helped the model slightly. Okay, so this is a very, very small change, right? We went from 19.28 to 19.21. So really not a very big improvement, okay? But technically it did improve the predictions slightly. Using the time exogenous features that we created, so from using Fourier series and from the date stamp, did not help the model in this case. It's even worse than not using features at all. But in any case, right, it is better than seasonal naive and better than ARIMA. All right. So that's it. This is how you can include exogenous features in your models. So the next step is going to be doing prediction intervals to quantify uncertainty. All right, so up until now, we have done what we call point forecasts. Okay, so we have only predicted, future values. But how do you quantify the uncertainty of your predictions? So point forecast is what we've done, right? It doesn't consider the uncertainty of the future. But the way to measure that is by using a prediction interval, which gives us a range of values associated to a certain probability that the actual value falls inside that range, right? So for example, with a 95% prediction interval, we expect the actual value to have a 95% chance of falling inside that interval, all right? Now, the neat part is that stochastic models inherently generate prediction intervals because uncertainty is embedded in themselves, right? And luckily for us, ARIMA is a stochastic model, right? It has that uncertainty parameter, that random error term embedded in its model. And so we can use the ARIMA model to generate predictions intervals right away, all right? So again, that's it. Super short, super short slides here. But then we're going to jump back into the code and see how we can generate prediction intervals with our ARIMA model. All right, so now let's run our forecast using prediction intervals. So once again, doing the same setup that I have done before. So selecting baguette and croissant, and then just making the train test split. All right, so now just to give you back an idea, our training set looks like this. And to generate predictions with prediction intervals is actually very simple with stats forecast. Okay, so again, we're going to define our models. So here, once again, is going to be the auto ARIMA model. Season length is going to be equal to 7. We're going to be using the unit price because we know this helps the model. This has been the best performing model up until now. And then when we initialize the stats forecast object, again, model is going to be equal to models. Frequency is going to be daily. And then we're going to fit on the training set. And now to make probabilistic predictions, so prob_pred is going to be equal to sf.predict. You specify your horizon. In this case, you need to specify the future values of your exogenous features, right? Because we are using the unit price. So this is going to be test.drop. So we're going to drop y like so. And then you simply need to specify the level argument and then pass the prediction interval that you want to have. So in this case, using level equal to 80, we will get the 80% prediction interval. And the neat part is you can pass multiple values, okay? So you can say 80, 90, and for example, 95. So now you will get 3 different prediction intervals, the 80%, 90%, 95% prediction interval, all right? Now, usually in most cases, I believe the 80% prediction interval is more than enough and very reasonable to have, right? Because again, if you start going to the 90, 95, 98, then those prediction intervals tend to be very large, and maybe it's going to be useful for anomaly detection, but really for forecasting, I think that sticking around the 80% level is more than enough and very reasonable, all right? So we are just going to run this, and that way we are going to be making predictions, but now they quantify the uncertainty, so we'll get a upper bound and lower bound. And as you can see, this is already done, so now we can merge this to evaluate, and then we can make some visualization to look at our probabilistic predictions. And we get the following. So now, as you can see, we get not only our point forecast, so the same forecast line that we have obtained earlier, but now we also have this shaded area around our forecast that indicates, this is the 80% prediction interval, meaning that, the actual value has an 80% chance of falling between the upper bound and the lower bound, okay? So now, of course, this has been, was to show you how you can make forecasts for the future and also compare against actual values. So now let's run cross-validation. So again, same model, same stats forecast object. So now we're just going to run cross-validation, but with probabilistic predictions. So CV prob df is going to be equal to sf dot cross validation. And I'll say that h is equal to horizon. Df is going to be equal to small df. And windows is equal to 8. Step size is going to be equal to 7, or the same thing as our horizon, right? and then refit is going to be equal to true. And now if you want your prediction intervals, simply set the level argument the same way that we did when we were doing the prediction above. All right, and our cross validation is done. So now we can once again plot the predictions if we want. So now, as you can see, we have made predictions over multiple windows, and we get the upper and lower bounds for each window. All right. Now, I am not evaluating those forecasts just yet, because when we are making forecasts with prediction intervals, we need to use different evaluation metrics, okay? So in this case, using the MAE is not appropriate anymore to evaluate our model with prediction intervals, all right? So let's stop here for now. We're gonna go back into the slides just to study some evaluation metrics, and then we'll come back here to make the final evaluation of our model. Okay, so we have only evaluated our performance up until now using the mean absolute error, okay? Super simple metric, easy to understand. However, there are other metrics that might be more appropriate for your project, and also your metric must match the kind of forecast that you're making, okay? So you might have noticed we did not evaluate our forecast with prediction intervals because we need a specific metric for that, okay? So for point forecast, okay, you can use different metrics, MAE, so mean absolute error, mean squared error, the root mean squared error, the symmetric mean absolute percentage error, or the MACE, which is the mean absolute scaled error, all right? Don't worry, I know I'm throwing a bunch of words right now. We're gonna define everything in just a second, all right? And for probabilistic forecasts, we need to use the CRPS, okay? This is generally a good option for probabilistic forecasts. So let's go into more details of all these acronyms that I threw around, all right? So for point forecasts, I like to stick with the MAE, SMAP, or MACE, okay? Those are usually my go-to. MAE, the mean absolute error, you know, it's robust to outliers. You care about all of the error sizes, and it has the same units as the data. So that's always super useful. So you can really say, you know, the model is on average off by like $10,000 or, you know, 10 gallons of milk, whatever, right? Super easy to understand. Then we have the symmetric mean absolute percentage error, or the SMAP, SMAPE. I don't know. I'm not really sure. I call it SMAP, call it SMAPE, whatever you want. This is cool because it's actually expressed as a percentage. So, you know, sometimes it's easier to understand a percentage. And, you know, this is basically an improved version of the MAPE, the mean absolute percentage error. But that one tends to, you know, favor under forecasting. So here with the SMAP, with the symmetric SMAPE, we are equally sensitive to over and under forecasting. So usually a better choice. However, you need to avoid that if your data is close to zero, right? So if your data has any zero values, then you know you're going to be doing a division by a very small number or a zero number. And so then your SMAPE is going to explode. So of course, avoid at all costs if your data ever goes to zero. And then we have the MACE, the mean absolute scaled error. This one is super interesting because basically it's like the mean absolute error, but scaled by the in-sample naive forecasts, okay? So this is super cool because your metric is already scaled. So if you're comparing series of, you know, one series is around in the 30, you know, values around 30, but then you have another series with values around 300 or 3000, right? The scale is very different. And so your MAE is going to be very different as well, right? For the series with a smaller scale, the MAE is going to be small. But for a series with a larger scale, obviously your MAE is going to be larger, right? So by using the MACE, you can then compare everything on the same scale because everything has already been basically divided by the in-sample naive forecast. And so, you know, that makes it really good to compare series of different scales. And you can also compare right away to the naive forecast, right? So if your value is less than 1, okay, so 0 point something, you already know that your model is better than the naive forecast. And then for the CRPS, right? So this is good for the probabilistic models. So it's a generalization of the mean absolute error. And here it compares the ground truth against a cumulative distribution function. So it's going to assess how well the predicted distribution aligns with the actual value, taking into account the central tendency and the spread of your distribution, basically. All right. The closer it is to 0, the better the model is. And so with all of that in mind, let's go back into the code, okay, and evaluate our forecasting models using all of the metrics that we discussed here. As you will see, it's going to be super simple. All right, so now let's take a look at the different evaluation metrics that you can use depending on the types of forecasts that you are doing. So here I already ran cross-validation using the auto ARIMA model. So here it's a seasonal ARIMA model using the exogenous feature, so the price in this case, and I am comparing it to the seasonal naive, okay? Simply because, we know that now that SARIMA with exogenous features is the best model. So I ran cross-validation using the level argument. So now we have this final cross-validation data frame where we have the actual values, the predictions from SARIMA and seasonal naive, as well as the lower and upper bounds for the 80% prediction interval for both SARIMA and seasonal naive. All right. So now we have all of the information that we need to run the evaluation metrics and evaluate both our point forecasts. So this is what is stored in SARIMA exog and seasonal naive column, as well as the probabilistic forecasts. So using the upper and lower bounds for both methods, SARIMA and seasonal naive. Now, there is just one last thing that we need to do before evaluating using all of the metrics that we described in the slides, which is to define a temporary testing and train data set, because if you recall the MACE metric, so the mean absolute scaled error, this error is scaled by the in-sample naive forecast. Therefore, to calculate that, we need to pass a training data frame. Okay, so we need to pass some kind of data to do the in-sample naive forecast and then scale the mean absolute error. All right. So I'm going to say that temporary test is going to be equal to small df dot group by. We're going to group by unique ID, and then the tail is going to be equal 7 times 8. Why am I doing that? Is because I ran cross-validation on 8 windows of 7 time steps. So I'm just going to take the initial training set, right? So everything except the last 7 times 8 time steps, just to make sure that I am not using data that wasn't seen by the model at some point. So that would be a bit of cheating. So then temp train is going to be everything else. So small df dot drop test dot index, and then we're going to reset the index. Perfect. All right. And then once that this is done, we can evaluate using all of the metrics that we described. And it is super simple using utils forecast. So I'm just going to specify the name of the models that I want to evaluate, which is SARIMA exog and seasonal naive, like so. So of course, this has to correspond to the name of your columns, right? So SARIMA exog and seasonal naive. So that way, I don't have to drop the cutoff column. Okay, so either you drop the cutoff column or you specify the list of models. And then for the metrics, luckily for us, utils forecast has all of the metrics that we discussed, okay? So we can use the MAE, the MSE, the RMSE, so the root mean squared error. You can use the mean absolute percentage error, symmetric mean absolute percentage error. If you want to use the MACE, you need to use the partial from functools, and then you pass the MACE and you set the seasonality. So in this case, seasonality is going to be equal to 7, all right? And then you can also use the scaled CRPS. So here in this case, I know we discussed the CRPS directly, but with utils forecast, it is scaled already. So you can compare series with different scales immediately. So then you can say that final eval is going to be equal to evaluate. And then you can pass the final CVDF just gonna drop the DS and cutoff columns. Axis is equal to 1. And then the metrics is gonna be all of the metrics that we defined above. Let's not forget the comma. And then after that, I will say that the models is equal to models. Train df, this one we need to pass because of the MACE metric that we want to measure. Otherwise, we don't need to pass this. And then we also specify the level, because here to calculate the CRPS, we need to pass the level argument. And so specifying the level of 80, evaluate function will immediately look for the upper and lower bound corresponding to the 80% prediction interval. Okay, so it's going to look for Surima exage low 80, Surima exage high 80. Okay, this is done automatically when you specify the level argument. Great, and then once that this is done, you can of course do a global evaluation by taking the average across all of the series. So final eval dot drop the unique ID axis equal 1, and then you're gonna group by the metric, and then after that you're gonna take the mean, and then you're gonna reset the index, and then you can take a look at final eval. And then once we run this, you should get the following data frame, which evaluates again the performance of our models using all of the series that we specified earlier. All right. And then you can make a small visualization. So sorry about that. I forgot to define the colors list. So once you run that, you should get the following graph. And as you can see now, we get the a visualization of all of our metrics for our series. So here again, the MAE better for Surima, okay, because it is lower. Then we can have the MSE, so the mean squared error. Like I said, this one a bit hard to interpret, right, because all of the errors are squared. Then we can have the SMAP, which is basically the symmetric version of the map or the MAPE, okay? So this is, in my opinion, a better metric than the MAPE, okay? And however, we have to be careful because sometimes our data, it was close to 0. So maybe not very super equal to 0, but it might have been close to 0. So again, we have to be careful with those types of metrics when using data that is close to 0, because again, you might divide by a super small number, so it makes everything explode. However, it is cool because it is already scaled, it's expressed as a percentage, so very easy to understand. Then we have the RMSE, so it's just bringing the MSE back to the original values. Usually it's going to be higher than the MAE. It makes sense because it is still penalizing large errors, more heavily than the MAE. And then we have the MACE. Interestingly here, the MACE is above 1. So this metric is technically telling you that our models are worse than the naive forecast. However, we have to be careful because this is scaled by the in-sample naive forecast. So it's not like we made forecasts with the naive model and then we scaled using that information. So this metric, again, it's a bit tricky to interpret. It is not true, right, that our models are worse than the naive forecast, but because of the way it is scaled, because it is using the in-sample naive, it's a little bit hard to compare that directly to the naive forecast. So anyway, don't really worry too much about the value being greater than 1. Here we can really see basically that Surima using exogenous features is better than seasonal naive. And now that metric is also scaled. So it's also easier to make that kind of comparison with series of different scales like we have been doing. And then the final one, the scaled CRPS. So once again, Surima, a better model than seasonal naive, all right? So I know I showed you a bunch of metrics. This is mostly to show you the kind of possibilities that you get with stats forecast and utils forecast. In this case, what you should really look at, in my opinion, is the MACE because it is already scaled, okay? So don't really worry that it is greater than 1. It doesn't mean that your model is worse than the naive forecast. But you can already see that Sarima is better. Scaled CRPS also useful when you are doing forecasts with prediction intervals. You get the sense that Sarima is better. In this case, the MAPE and SMAPE, not very useful because we have data that is close to zero, so we shouldn't be looking at them. The MAE, it's okay. However, do notice that your series have different scales. Okay, so there might be a bit of a bias in there. MSE, RMSE, in my opinion, the MSE is hard to interpret. The RMSE is fine. However, you still have this scale problem, and you are giving more importance to large errors. Whether it's something that you want or not, this is up to you to decide. So that's it. This is how you can evaluate your models using different metrics. Congratulations on making it this far. You have done a lot. You have learned a lot as well. I am super proud of you. I hope that you are proud of yourself. But now, what's next? Okay, where do we go from here? So of course, I could not cover everything in a single video. And if you watched it this far, then it probably means that you are serious about mastering time series forecasting. And I think that you enjoy my way of teaching and presenting this material, right? And so for all of those reasons, what I think the next best step is for you is basically taking my course, Applied Time Series Forecasting in Python, okay? This course is basically, it allows you to master the forecasting field in 3 months, okay, by doing one lesson per day. Okay, we use 100% Python code, and so we're going to take a look at more statistical models. So all the statistical models that I mentioned earlier, we're going to cover them in this course. We'll take a look at the deep learning models for forecasting. We're going to implement the state-of-the-art models, okay, so the very latest advances in the field. I cover them. I update this module often in my course so that you can stay up to date and relevant in the field. We'll also take a look at how we can forecast intermittent time series, okay? And so throughout the course, you are going to build a portfolio of forecasting projects, which basically acts as the best proof of your skills and knowledge so that you are ready to impress either at work or during an interview if you are trying to, to switch careers or, you want to transition into the field of forecasting. This course really is going to help you for that. And of course, I will be there every step of the way. So any questions that you might have, you can ask them, below each of the videos in the course. I personally read them and answer them every day. All right. So I am there to help you and to really guide you into learning and mastering time series forecasting. So if you're really serious about it, you want to learn how to do it, you want to keep up with the latest advances, okay, in the field, and you want help to get there, then check out the link under this video, and I will have a massive discount for you when you enroll, because you watch this video entirely, you're ready to take the next steps, and I want to help you in that. So once again, thank you so much for watching. Good job on completing this video, and I will see you in the next one.